Press the bell icon on YouTube and don't miss another update.
Namaste, and I welcome all of you to this session of weekly dialogues in Jaipur Dialogues. And I have Dr. C.K. Raju again, and this is the fifth session on the history of science and mathematics in India. We had been discussing the transmission of various branches of mathematics to Europe from India. And in this session, we'll continue discussing the transmission and we'll also move on to the applications as they took place in Europe and how they did not acknowledge their debt to India. Namaste, Dr. Raju. Sir, we discussed the transmission of various branches of mathematics, and we've got other branches like calculus, like astronomy, that also need to be discussed. We have that appropriation model, the discovery model that the European used, and we also have the Cartesian and Newtonian mathematics that almost completely plagiarized Indian mathematics but did not own it up. So for all this, in this concluding session, I welcome you, and let us move on to the calculation transmission.
Yeah, okay. So this is just a little bit more difficult to understand. The principles are exactly the same. Principle is that what I call the epistemic test. And simple way of putting it is that, as a teacher, you often come across students who cheat. So you get answer sheets which are very similar. And then how do you decide who has cheated? And how do you prove that somebody has cheated? They will all deny it. We didn't cheat. So how do you do it? So one of the ways is that you call the student and ask the student to explain what has been written. You understand what has been written. To demonstrate your understanding, you answer a few questions. And the person who cannot answer has obviously not understood what he has written, has cheated. So this is one of the tests of transmission that I had. And epistemic test. There were other simpler things, like how do you establish that a murder has taken place? You look at motive, you look at opportunity. So we look at motive for transmission. Why would somebody want to steal, let us say, the calculus or arithmetic? Because it has a certain practical advantage. And then the question is, did they have the opportunity? The answer again is yes. So the Jesuits had a college in Cochin. They were translating all sorts of local texts, and they had the assistance of local people, the Syrian Christians particularly, and they were using that to get a whole lot of information and transmit it. And it's a standard church model which was used in Toledo to appropriate from the Arabs and say this was all done by Greeks, it's all our inheritance, we are taking it back. Suddenly we realized this is our inheritance and we took it. So this was the opportunity was there, the motivation was there, that the navigational problem, it was the biggest problem in Europe. See, all your Royal Society, French Royal Academy, etc., all started around the navigational problem. And the governments in Europe, this is not something that can be denied. Governments in Europe from the 16th century onwards, they were offering huge prizes. And the last such prize was offered in the early 18th century. It was the Longitude Prize, and it was Board of Longitude was set up by a British Act of Parliament. So you can understand how important it is. You see, if you have an Act of Parliament to solve a mathematical problem, and the reason they could not solve
the year 1718, I think.
1712, 1713. Yeah.
Okay.
And yeah, that's when the Board of Longitude was set up. So it was because after all, the entire wealth depended on that. See, if a ship sinks, which is carrying treasure, so many people gone, so much money gone, much more than happens in a normal war. So it was a big issue. And that is why the Parliament addressed it, and that is why they set it up. And they solved it in a slightly different way from what was done in India. The reason was they did not understand the Indian methods of determining longitude. Why not? Because it required a certain parameter, namely the size of the Earth, the radius of the Earth. And we were talking about trigonometric values precisely. So they stole the trigonometric values. Clavius put down the Indian trigonometric values in his name in 1607. But he did not understand. See, that's the epistemic test. He can say, I got it. He can say, nobody, I had something, some divine inspiration, whatever. I got exactly the same number and so on and so forth. But he did not understand, because if he had understood, he would have been able to calculate the size of the Earth, which he was not able to. And therefore, there was a longitude problem, because as I keep repeating, as Brahmagupta said, no, bhuvyasasya agyanat vyartham deshantaram. So you don't know the radius of the Earth. How are you going to calculate the shanta, which is the longitude? It is vyarth to do it. And that is precisely the problem they had. And so they eventually developed a new technology of the chronometer, which then by the end of the 18th century, they managed to do this. But for everything, the Mercator chart, etc., they had to use the trigonometric values from India. Now, I also looked at some other things like, circumstantial evidence. And I think I should quickly cover that. I have it somewhere here, maybe in this. Circumstantial evidence should be here. Ferma. Where is Ferma 1? This is the version 2. Yes, it should be here. Yeah, here is the Ferma problem. So, Ferma, he was a famous European mathematician, French mathematician. And he wrote, this is the reference. This is his collected works, page 332, 1657. So he posed a challenge problem. He posed a challenge problem to European mathematicians, which nobody was able to solve until Euler did so in the 18th century, and he had access to Indian texts. And the interesting thing is, this is a problem totally copied from Bhaskar's Bijganit. And this is the reference to Bhaskar's Bijganit. It is 87. It is there in the Colebrook translation. You can find any other translation, right? Bhaskar himself poses it as a sort of a challenge problem. Now the point is, let us forget about what the exact thing was. The problem looks simple. If you are trying to find, for a given n, you are trying to find solutions of nx squared plus 1 equal to y squared. But for a reasonably large value of n, the so-called Pell's equation, nothing to do with Pell, the numbers are very large. So you see, this is one number, it's a very large number, and this is another number. Wait a minute, am I showing the screen or not?
Not yet.
Oh my God. I forget. You should please remind me. Let me come back. I should have shared the screen. I'm sorry. I am becoming old. I make these kinds of mistakes. So please remind me when I make such mistakes. Okay,
Never
so
mind.
this is the, yeah, okay. So this is the screen I was sharing. This is the reference I gave. Are you able to see it now?
Yes.
Yes. So this is the reference, February 1657. This is the reference to Ferma I gave. And this is copied from Bhaskar's Bijganit, verse 87. This is the reference that I gave. And the problem itself is quite simple, to find solutions x and y for a given n. And Fermat took the value of n equal to 61, and he posed this as a challenge problem for all European mathematicians. Nobody was able to solve it. Reason is that the solution, the numbers involved are very large. So you can see this is one number, and you can see this is a second number. Now, what is the probability of a coincidence? Exactly this problem is found in Bhaskar too, centuries earlier. Exactly those numbers. There are such large numbers. How can they be independently rediscovered just when independent discovery is possible? Just when the Europeans have been in India for 1.5 centuries and they are collecting information, and then they will say, "Oh, it's all independently." How can it be? It's complete nonsense. So it's very strong, compelling circumstantial evidence. All right. So this is the kind of circumstantial evidence. But let's go again to the question of the epistemic test. Now, when we try to understand how is it that, first of all, there are two things. We are told that Newton and Leibniz discovered the calculus. Now, what is this discovery? I think I had given you earlier. See, Newton himself, what did he claim? Newton claimed that he had discovered the sine series. The same sine series which I showed you earlier. Let me see if it is there here. It should be in. Where is it gone? It's not in this. Wait a minute. Let me switch to.
It's okay. We have already seen in the previous session.
Oh, you've seen that. All right. So it is the sine series, so-called Taylor expansion for the sine. And he claimed that. And then there is the so-called Leibniz series for pi, which again is found in India so many centuries earlier. So there is absolutely no doubt. Yeah. The Madhav values are from there. And everything can be found, for example, in the Yukti Deepika. All right, and I use Yukti Deepika because if you go to palm leaf manuscripts, they're difficult to access and so on. Here you have a printed text, and then there may be variation in one manuscript and another. Here you have a critical edition. All right, so it's a critical edition by K.V. Sharma. So let's get back to this. So the so-called Leibniz series was discovered by Leibniz. So-called, how are they able to discover? Now, I think we need to understand one meaning of the term discovery. So maybe I can do this doctrine of Christian discovery. Let me search for let's see. Yeah, here it is. Managed to get it. Meaning of Christian discovery. So here is this article. What does this word discovery mean? There's also a video, as you saw in the Google search, but I think the video didn't probably put down all the facts. So this doctrine of discovery is a very obnoxious doctrine. See, when they say Vasco da Gama discovered India, where were we? I mean, Vasco da Gama discovered India, where were we? So he didn't discover the sea route to India. Obviously not. We were trading with the Romans, for example, for 2,000 years. There are hordes of Roman coins and so on and so forth. So this route to Africa, sea route to Africa is also known. There's nothing discovered, but the word discovery has a technical meaning. And the technical meaning is that the first Christian to discover something becomes its owner. To discover a piece of land becomes its owner. When they say Columbus discovered America, then they say that Cook discovered Australia. There were people, millions of people living there. What happened to them? What happened to them was that according to the European laws, according to British law in particular, according to currently existing US law, they lost their right to land. Not that they thought in terms of land ownership, but they lost that right. All right, and this is the reference to the US Supreme Court judgment, which there were two bulls, papal bulls were there, which were the bull Inter Cetera and the bull Romanus Pontifex, and they are referred to here. And there is a U.S. Supreme Court judgment on that. This is the U.S. Supreme Court judgment, which is still valid.
Yes, I think 19th century.
Yes, 19th century, because one of those so-called Red Indians, he challenged he said that, look, this land was ours, give it back to us. So what is your sense of justice? He thought he will get justice by going to court. So he was a bit naive. So he went and tried, and this is what the judge said, that although the Protestants, that the Pope passed the bill, but Britain accepted it, and they had this principle of discovery. So the first Christian to spot a piece of land or knowledge becomes its discoverer. And that
And
is
owner.
and owner. And this is something extremely obnoxious because you see, this is the principle of genocide. You see the description. This is a description given by Las Casas, who went with Columbus. This is the kind of description that he gives, how they just murdered people, not sparing children, not the aged, not pregnant women. They murdered 10 million people in his estimate. Much more than all those people who are supposed to have been killed in the Second World War, all those Jews and so on. You accuse Hitler of genocide. It's not even half of that, because but this is what happened immediately in Las Casas' lifetime. That is his estimate, a short account of the destruction of the Indies. So they killed so many of them, killed them in the most brutal manner, and killed them for religious reasons. So this is the principle of discovery, that if a Christian comes across a piece of knowledge, it becomes his. And that's the sense in which Newton and Leibniz use the word discovery. So what?
Right, exactly. Okay.
Newton said that, right, this is the idea of discovery. So he
What
called
about discovery of India?
That's Vasco da Gama. I have a little video on that, so please take a look.
No, Discovery of India, the book written by Jawaharlal Nehru. I mean, he
Yeah,
also
but I have a different version of Discovery of India.
discovered and owned India.
Yes, exactly. That is what I learned in school. I went to Anglo-Indian school, and they were using those British books, and they were teaching this idea of discovery of India. I said, Vasco da Gama discovered India, and I didn't understand. I said, where were we before we were discovered? And the teacher could not explain. He said, we are right here. I said, then what did he discover? And the problem is, it is still being taught in Africa. And if you tell people, why are you teaching this nonsense about discovery? They get very suspicious. Who is this guy? What is he saying? Hurry, discovery is such glorious acts. So these are the glorious acts of genocide. So genocide is one aspect of it. Epistemicide is the other aspect of it, when they steal knowledge. All right. So there are two principles. There is discovery. And the second thing is discovery without understanding. We saw that in the whole lot of simple cases. The same thing happened in the case of calculus. That Newton and Leibniz and so on did not understand it. In fact, it was not understood till the 19th century, certainly. Now people will say, no, okay, maybe in the end of the 19th century, look, how can you discover something? How could Newton and Leibniz have discovered something if the understanding came only 2 centuries after them? Ridiculous. But even in the 19th century, the understanding didn't come. They'll say, oh, Dedekind did it, because Dedekind was teaching, and he said it is complete nonsense. This is not making any sense to me, but I will try to solve the problem. And he discovered something called Dedekind cuts, and Cauchy did something. And now you'll say, and we teach Dedekind cuts today. So you say, okay, the problem was solved. The problem was not solved. It's a complete myth. Because even with Dedekind cuts, or even with Cauchy sequences, the problem is not solved, because you need something called the real number system. Formal real numbers. Now, I will tell you why. What was the problem? Why I had this problem? Because there were certain, before I get into a discussion of formal real numbers, which is a little bit abstract, little bit difficult. So the simple difference, philosophical difference between Western understanding of math and the Indian understanding of math was, I think that is what we need to look at. And this difference was that in the Western understanding, mathematics was exact. In Newton's understanding, he had the superstition that God has made the laws of nature. That's a principle made by Aquinas. And then he said that God has made the laws of nature, and these laws of nature are written in the perfect language of mathematics. So this, I think I can stop the screen sharing for the time. And this was the idea that Newton had, that he would, he must do it perfectly. Now the problem that arises is, if you have an infinite series, for example, an infinite series for root 2, or we saw the infinite sine series, how do you sum it? That's the question. Now, there was some system of summing it in India which was available. Let me just quickly give that. But the basic difference was that in India, people accepted inexactitude. In the Shulva Sutra, in various things, inexactitude was accepted. And for example, you talk of Savishesh. Maybe just take a look at this paper. I think it is the second one. Let me just check. I think it's the second one, maybe the first one. Calculus transmission. No, it's the first one. So, first one, let me share the screen now. Okay, share screen. All right, let me quickly give an example of that. Okay, here we are. So this is in Neelkant's Aryabhatiya Bhashya. This is the sum of an infinite geometric series. Are you able to see this?
Yes.
Okay, so this is the shlok in which he gives the sum of an infinite geometric series. And we know what the formula is. It's not very difficult to get the formula. The point is, finite geometric series has been known for a very long time. Finite geometric series is found in the Rig Veda, Yajurveda. You also find finite geometric series in Egypt in the so-called Eye of Horus fraction. So these are very old. But the infinite geometric series makes its appearance for the first time here, and there is a sum, finite sum that is given to it. So it is the same. I mean, this is a formula that people remember from school for the finite, for the infinite geometric series. All right. So there is nothing, but the question is, how do you sum it without the notion of limit? How do you sum it without the notion of real number? So these notions did not exist in Europe until about, well, the 20th century to be very precise. Middle of the 20th century, when you had real numbers, when Dedekind cuts were given proper shape using set theory and so on. And the basic difference is that Western mathematics wants to be exact. And it is exactly the system of real numbers you want, nothing less, nothing more will do. Because if you have a larger system, then it is what is called non-Archimedean. So Cauchy sequences will not all converge. Some may converge, some may not converge. If you have a smaller system, again the same problem. It must be exactly that. And it's a huge infinite system. So it's a metaphysics of infinity that you create in order to get exactitude, which is something wrong. Because in India, what was done was different. But Brahmagupta started long back the idea of polynomial arithmetic. He had what is called avyak numbers. So this is described in this article. It's available online. It's available also from my website. It's available at Stinger. And if you want to know about non-Archimedean fields, there is a book by Moyse at an elementary level. So the point is that in a non-Archimedean field, you will have numbers for which x greater than n, at least one number x, such that x greater than n for every n. That's the idea of an infinite number, very large number, greater than n. This can happen in a polynomial arithmetic. If I have a number, let us say 2x plus 3, is it, can I say that 2x plus 3 is less than 4? I cannot say that, right? Because x may have any value, it depends on what x is. And because it is, you can do polynomial arithmetic just like any other kind of arithmetic. So you can also divide and so on. So if you have infinitely large numbers, you'll have infinitely small numbers and so on. So this was the system that was used. And once you have that, you can discard infinitesimals. Once you have infinitesimals, that is exactly the process that was used to sum infinite series in India. But the Europeans didn't understand it. And they had this idea. Newton particularly thought he had got the laws of God had been revealed to him. And because they had been revealed to him, he wanted calculus to be perfect. To make it perfect, he said something, he talked of fluxions. What are fluxions? Nobody understood what fluxions are. Please take a look at my book. They are discussed there in complete detail, also in some recent articles. So Newton did not have a way to sum infinite series. Nobody had a way of doing that in Europe. But
you're talking about Kevin picture time?
No, cultural foundations of mathematics.
Okay.
There's a chapter on which discusses Newton's theory of fluxions and how it went wrong. And there are also some recent articles which discuss that, right? So this is the crux of the matter, that because of the Western superstition, that God has made the laws of nature and those laws are written in the perfect language of mathematics, so everything should be exact. And Newton thought it is important that everything be exact. What he did was, because he couldn't make sense, what are these fluxions? It's about time. So he said time must be made metaphysical. That is what he did, making time metaphysical, and that sort of, he lost the point there. That is the reason why Newtonian physics failed. Okay, so
he also propounded the theory of linear time.
No, he propounded the theory of metaphysical time. You see, what he said in his book, Principia, he said that absolute, true, and mathematical time flows on without regard to anything external. So he is using so many adjectives: absolute, true, mathematical, and without regard to anything external. So he is making clear that this time has nothing to do with any physics. I'm not able to measure time accurately. What is meant by equal intervals of time? Not able to explain. What is the clock which will measure it? He's not able to explain. That doesn't matter. God knows and I know that's enough. That's not all right. You need to know. Physicists also need to know. So there was a problem there. Now, I think that that is one part of it, but we also need to look at another part of it, which is things like the astronomical model. Now we hear these grand stories, right, from the time of Macaulay. Oh, we had such great astronomical models. Astronomical models also went from India. So you have Nilkant's astronomical model, and which is Tycho Brahe copy. Tycho Brahe was the other top Jesuit. He was the royal astronomer to the Holy Roman Empire. And let me show you what Tycho Brahe, what the model was. Because we hear about Kepler, we hear about Copernicus, and so on. And I just want to give a couple of those things here that, I didn't check whether this can be shown. Okay. Let me, let me just check this. All right, so let me show you this. Now, I'm not sure if I can share the screen. Let me, application, it is there. Now, let us see if you can see it. Can you see it?
Yes.
Very good. Excellent. So this is the system which you learn in school. You have the sun at the center and various things going round and so on, right? And this is, you could say, based on the Keplerian model, which is supposed to be the great thing that was done. But let me show you now Nilkant's model. And Nilkant's model, I would like to know what exactly is the difference you find. So let me share the screen. Share screen, application window. So this is the so-called Titanic Cosmology. So what's the difference? The difference is that all the planets are going around the sun, but the sun with all the planets is going around the earth. But the difference is only visual if I draw it against a fixed background. Otherwise, you can't say here whether the earth is going around the sun or the sun is going around the earth. See, unless I put my cursor there at some point, and which of these things is not moving. So you see, this point is not moving. Then I say, okay, sun is going around.
Screen, I can't see.
You can't see?
It's come on now. Okay.
Okay, I'm so sorry. So I'm saying, what is going on? Are these bodies going around the yellow sun, or is it the other way around? So unless I put my cursor there, I have some external point of reference. I look at this earth, I say, okay, earth is fixed because my cursor is fixed. Otherwise, it looks just as if it is going on. There is no difference. In fact, there is no scientific difference between this model and the Keplerian model. It is just a big, huge story. And they will say, heliocentric, what a great advance. Heliocentricity is not a fact. Let me show you something called the two-body problem of Newtonian physics. All right, let me show this to you. Okay, so I want to share this application. Yeah, that's the one. Can you see these two little balls?
Waiting.
Okay.
Yes, come on. It has come on.
Great. So, see, they don't, one ball doesn't go around the other. Both of them go around a common center of mass. It's barycentric motion. Sun is not stationary. Don't for a moment imagine that it is a fact. Quite apart from the fact that Copernican model was taken from Ibn Shatir, we are just looking at this big story of heliocentricity. It did nothing. The Titanic model and the heliocentric model have exactly the same consequences, and in order to check those consequences, you have to make measurements sitting on the earth. Well, nowadays maybe you can go out, but at that point of time you had to do it by sitting on the earth. So here you see, this is what you actually see, that they are two bodies going around a common center of mass. It is barycentric motion, and of course the sun is not stationary. Sun is going around the galaxy at a very high velocity, and those are just big stories. And so the problem is that we have had a surfeit of those stories. Neil Kant's model was a very good model, and we just fall into Macaulay's rhetoric and say, oh, it must be, guy must be great, and what he was did, and so on and so forth. So that's not on. So I think I made 2 points, that because Newton did not understand calculus, therefore his physics failed. What was the problem with Newtonian physics? The problem was that he made time metaphysical. So what was the correction? You had to have a physical measure of time. You had to actually define a clock which can be used physically instead of just saying absolute true and mathematical time. That was done by Poincaré. But of course, the Western world is so crooked that Einstein took the credit for it. So it is the same old story. And the point is, it's the same old story which works. Einstein took the credit, but he didn't understand the theory of relativity. Such a big God has been created, totally false God. But this is the character of the way they erect such big structures. Fellow didn't understand the theory of relativity. Say, it is not that he stole from me. He did not steal from me. Somebody else stole from me. But Einstein didn't understand it, because if you have the theory of relativity, then things travel at a finite speed. So the light from the sun will take some time to come here. So you cannot have instantaneous action at a distance. You must have at least delayed action at a distance. Maybe something more complicated, but at least that. And if you have that, so-called functional differential equation changes the nature of physics. Poincaré understood. He was a mathematician. Einstein did not. But they made a great story of him. Oh, there's that. And so many people are heavily invested in it, and nobody would like to believe it. And they say, oh, if this guy says something, something must be wrong with him. Everybody else is saying that. But I understand. And the most interesting part is that the doctrine of discovery is still going on in both cases. The calculus also, somebody from Manchester, absolute thieves. Again and again and again, they stole, plagiarized an entire paper. And the theory of relativity, where I corrected Einstein, top mathematician in the world, Michael Atiyah, was the president of the Royal Society. He took it up and did it again and again, 2 times. And everybody supports him. Mathematical society will support him. They won't say a word. They will talk big about ethics, but they won't do it. So the point is, whatever may be your ethics, your lack of understanding shows. And therefore, you have to change things. You have to change the way you do mathematics. You have to change the, why should you have limits? Why should you have this? There's a much simpler solution in India. And therefore, you should teach calculus that way. That is what I'm trying to do. But you see, if people don't understand, where Sarkar is going to understand? They don't know.
We will keep trying regardless.
At least some people have understood that is good enough. And so There is a much simpler way of doing calculus. We don't have to imitate any of this. We can go back to our way of doing it and teach it. And there would be corresponding changes in physics, and so many other changes are needed. But if you believe that the West is our my baap, it's very difficult for people to change. That's what our education system teaches. Most unfortunate, but that is how it goes on, and they understand that people are dependent. They understand that they can be manipulated. They understand that almost any nonsense they can, because that's why they cheat so brazenly. That's why Atiyah cheated so brazenly. That's why my book Cultural Foundations was also repeatedly plagiarized. So I think that these are some of the issues that, well, I personally had to face, but think of the society at large. It is terrible that we are following an inferior system when we had developed a better system here. And we can't even compare the two. Nobody even able to compare the two. It is so shameful.
You are absolutely right. But then I think at least now there's some understanding coming, and I think the truth is dawning upon people, and we have some movement, and even some foreigners are coming to the fore and declaring that Indian mathematics is the best and that is the way to teach. And
we need to do it at the level of calculus, at the higher level. Unless you do it at the higher level, it is not going to make any change. Because it's only when you throw, let us sit and compare. Let's have a public meeting and compare. We don't have that much of resources. We can't do this publicly. We are so scared. So nobody has their proper knowledge. If I ask people to do 1 plus, this is my challenge problem. Prove 1 plus 1 equal to 2 in real numbers without using any result from axiomatic set theory from first principle. Ask any professor of mathematics if they can do it. Just 1 plus 1 equal to 2, nothing more than that. Cape Town challenge. We only do.
Francis Bacon took 378 pages or something.
No, that was an integer. That's simple. This will take 1,000 pages. This is in real numbers. Okay. This is in formal real number that you are talking about, which are supposedly needed for calculus. So they will teach here this is needed, but they can't say what it is. It is really bad what the education system has done to us. Totally stopped us from thinking. At least we had a tradition of Shastra where people sat down and discussed and debated. So at least that should happen. Even that doesn't happen. It's only authority which will decide in secret. They can decide anything they like in secret and come up with any conclusion which is beneficial to them. Public discussion is what is needed, right?
So that brings us to the end of this series. And this was a very, very enlightening series. I'm sure that the discerning viewers that we have on Jaipur Dialogues would be immensely benefited by this discussion. And thank you very much, Dr. C.K. Raju. And because a lot of things that you tell people, people come back to us and ask us, okay, this is what we have not understood. And that will keep happening. So we'll keep coming back to you, sir. And thank you very much. It was absolutely wonderful having you here. And Vande Mataram, Jai Hind.